Hello class, this is section 8.4 and in this video we are going to discuss eigenfunction expansion using Green's formula. Once more we have a PDE with a non-homogeneous term and a term that does depend on time. This time we also have boundary conditions that are non-homogeneous and depend on time, and of course initial conditions. So we're going to try a slightly different method than we did in the past. Previously we first converted this problem into a problem with homogeneous boundary conditions, but it is possible to skip that step and go directly to eigenfunction expansion. So first, we ignore all the non-homogeneous parts to start with. This means not just the QXT, but also the AT and the BT here. And the goal is to get the eigenfunctions. This is a mistake, should be eigenfunctions. And we have Fn double prime x plus lambda n Fn x equals 0 as usual, because this will give us the Dirichlet boundary conditions, and these are 0. We know already what these are. So these are lambda n equals n pi over L squared, with Fn being the sine n pi x over L terms, but we'll ignore that for now. I want to emphasize this method works for any eigenfunctions. Oh yeah, but we do have the boundary conditions. Fn0 is 0 and Fnl is 0. Remember, because we were setting the non-homogeneous parts to be 0. Alright, and now that we have dealt with the eigenvalues, the eigenfunctions, we can go back to our original non-homogeneous problem. So we put back QXT, AT, and BT. The next step is to write down the eigenfunction expansion. So UXT is equal to the sum of n equals 1 to infinity. This time let's call the coefficients Bn, and they depend on time of course, since U depends on time, times Fnx. This is known as the eigenfunction expansion. Our goal, once more, is to find Bnt. The second step is to plug this eigenfunction expansion expression into the du dt part of the PDE. So remember, we stated in the past, for the t derivative, you could always do this in this class, that du dt is just going to be the sum of n equals 1 to infinity derivative of Bnt Fnx, that you could always differentiate u by differentiating every term of the infinite series. However, the x derivative does not work. You cannot just get the x derivative of u by taking the x derivative of the terms of its infinite series. We discussed this rule of thumb in the previous video, that this isn't allowed in this course if u and Fn don't obey the same boundary conditions, and these don't. Fn obeys the conditions Fn equals 0, Fnl equals 0, whereas u has these non-homogeneous boundary conditions. So we can't just plug in the x term, but let's just do the best we can. So we have the du dt term equals k times the derivative of x. So remember, we can't just plug this in. Let me just cross it out to emphasize it. This does not work. So we can't do that. So it stays as a u where it is, plus the QXT term, of course. But what this equation means is that the derivative of Bnt is the Fourier coefficient of the right-hand side. And we know the formula for the Fourier coefficients from chapter 2. This means that the derivative of Bnt is equal to the integral from 0 to L of this mess. Let me copy and paste, times Fnx dx over integral of 0L Fnx squared dx. Now if this looks unfamiliar to you, remember once again that the denominator is secretly L over 2. So you have 2 over L, and that's the exact same formula that you're familiar with. But anyway, we have this formula for the derivative of Bnt, and let's simplify this a little bit. The nastiest part of this formula really is this second derivative of uxt term, but it turns out that we can use the Green's formula to simplify the right hand side by getting rid of that term. So the term is second derivative of u with respect to x times the Fnx thing here. So when we distribute that, we have to get rid of this really ugly expression. It turns out that Green's formula from a few classes ago is going to be useful. And for our context, we want the operator curly L to be the second derivative with respect to x squared. And since we are just using a very basic equation, px is equal to 1. If you treat this as a Sturm-Liouville equation, px is indeed equal to 1. And we also we want v to be equal to fn. Once we make this simplification, we can indeed write down a different expression for our u double prime f term. And this is what we have. So the lu times v is equal to u lv minus px u dv minus v du. Oh yeah, v is f of course. Let me fix that. And okay, so let's try to simplify this expression. So there are a few simplifications we can make. First of all, remember that we have f double prime nx plus lambda n fnx equals 0. That's the eigenvalue equation. So in particular, this first term we can change to 0 to L uxt minus lambda n fnx dx. And this term, we can plug things in. You can get minus u L f prime n L plus fn L u prime L plus u0 f prime n 0 plus fn 0 u prime 0. However, please remember that the fn's also satisfy these boundary conditions, fn equals 0, fn L is equals 0. So these two go away. You're left with these. This again simplifies, and we have u0 is equal to at and ult is equal to bt. So in particular, we can change that too. This is going to be at and this is going to be bt. And when all dust settles, this is what we're left with. Let's see what we can do about this ufn term. We can do a little bit more of that term too. And one thing to notice is that from the eigenfunction equation, uxt equals sum from n equals 1 infinity bnt fnx, bnt are actually the Fourier coefficients of uxt. But this means that we have this nice formula for bnt, and this allows us to convert this expression into minus lambda n bnt times that fn squared term. So when we plug everything in for this expression, so now we have a simple expression for u double prime fx, and it's this one, we get this expression for bn prime nb n. And let's replace this with our expression for u double prime fn. Alright, and what we have is that the d dt bnt is equal to, so here we have a minus lambda n bnt, and the fn squared term cancels in the bottom. So we just have minus lambda n, and the k term of course stays, k lambda n bnt. We then have the bt and the at term over here. So this gets us minus bt fn prime L plus at fn prime 0. And this one has to have an integral of 0L fn x squared dx in the bottom. Now let's be a bit more careful. There should be plus that, plus minus this. Plus qxt fnx over that thing again, 0L fn squared x dx. Now this seems terrible, but we can solve this using integrating factors, and to do that we really should move this term to the left as well. This becomes plus equals that, and then we have an integrating factor e k lambda nt. And to do that, to solve the problem, we actually need an initial condition too. Comes from the initial condition of our original problem, ux0 equals fx. So we have that fx is equal to ux0 equals to sum n equals 1 to infinity bn0 fnx, which implies that the bn0 are the Fourier coefficients of little fx. So we know what the bn of 0 are, and bn0 is our initial condition for this problem, and we can solve the ODE using integrating factors and